DiffThinker towards generative multimodal reasoning with diffusion models. This is a new paper that really presents a fundamental re-architecture for how we think about vision problems in AI. If you follow MLLMs at all, you need to hear this.
It's definitely shaking things up. For a while now, models like GPT-5 and Gemini-3-Flash have all relied on text-centric reasoning. It's all sequential steps, chain of thought, these long text descriptions of what they're doing.
Which leads to huge latency and, frankly, pretty bad performance on complex visual tasks.
Yeah, exactly. And so the solution here is what's so radical. DiffThinker creates this whole new paradigm. Generative multimodal reasoning.
It's reformulating the task as a native image-to-image process. So forget writing out the steps. DiffThinker just paints a solution.
And the results back it up immediately. DiffThinker just blows the leading models out of the water across 4 really critical domains. We're talking sequential planning, combinatorial optimization,
constraint satisfaction, and spatial configuration. The performance gains are, well, they're huge. Over 314% better than GPT-5 and 111% over Gemini-3-Flash.
And beyond just the accuracy, this new way of doing things has these core advantages MLLMs can't really touch right now. It's more efficient, it's controllable in a fixed-step way, and it has native parallelism.
To really get why that's so powerful, I think we first have to dig into why the current state of the art, these big sequential text-first models, have been failing so badly in the visual space.
Right. It's what the paper calls a paradigm clash. For years, we've treated multimodal reasoning like it's a text problem that just happens to have an image attached.
Yeah, you feed the model an image and a goal, and you expect it to spit out this long text trace, the chain of thought, that hopefully leads to the right answer.
It's like asking an architect to describe a building one brick at a time instead of just showing you the blueprint. You're forcing this inherently parallel spatial information into a linear string of text.
And for simple things, okay, that works fine. But as soon as the task gets visually complex, like a big maze or a tricky puzzle, that text trace becomes a massive bottleneck.
It really does. The model is trying to track the changing state of a visual scene using just abstract symbols. And that's where the system just completely breaks down.
We did see some attempts to fix this, right? The thinking with image models.
Yeah, where the model could do multi-turn interactions, maybe call a tool to generate an intermediate image to check its own work.
But that just adds more steps, more latency, more computational cost.
Exactly. It's just patching the problem. The moment the task is what they call complex, long-horizon, vision-centric, the whole text-first approach just collapses.
And we see it in the data. We'll get to it later. But you see these top models dropping to literally 0% accuracy on the harder visual planning tasks. That's not a small dip. That's the model completely losing the plot.
The basic problem is if your medium for reasoning is sequential text, you're always going to be limited by that sequential nature when you're dealing with spatial things that are, holistic and parallel.
Which brings us back to DiffThinker. It just steps completely outside that symbolic text space. So for people used to MLLMs, this image-to-image idea, it sounds almost backward. Why is that the secret sauce?
Because it lets the model play to its strengths right from the very start. It's a vision model, so let it think visually. Instead of outputting go down, turn left, it produces a single image that shows the whole solution path at once.
So for a Sudoku puzzle, the output isn't a string of numbers. The output is the solved grid as an image.
Precisely. Or for the traveling salesperson problem, it's the image with the shortest route drawn on it.
Okay, but how do you evaluate that fairly? You can't just ask another MLLM if the picture looks right.
Good point. And they thought of that. They introduced what they call a parsing function, basically a visual parser. It takes the generated solution image and converts it back into a symbolic answer format.
So you can do a direct objective comparison to the ground truth. That's clever. It keeps the evaluation rigorous. But wait, if it's generating an image with a diffusion model, aren't those notoriously slow? How is this thing not incredibly computationally heavy? What's going on under the hood?
That's a super valid question, and the architecture is really key here. It's built on an existing image editing framework, but the engine is a 20 billion parameter multimodal diffusion transformer, an MMDIT.
Okay, so like the models behind DLE or Midjourney, but specialized.
Right. It's designed specifically to capture those cross-modal dependencies, the link between the visual input and the intended visual solution, all within its own latent space.
And the paper talks a lot about flow matching as the training framework. Why is
Yeah.
that important?
Flow matching is all about stability. Instead of the noisy, sometimes hard to train traditional diffusion methods, flow matching basically learns a smooth, continuous path from pure random noise to the clean solution image.
So it's a more predictable process.
Much more. It uses ordinary differential equations, ODEs, to define this path, which makes the whole learning dynamic really stable. It's about making the process less chaotic and more like a controlled transformation.
And for inference, you're not just taking random shots in the dark.
No, not at all. Reasoning becomes this controlled, deterministic process. They use something like a first-order Euler solver to basically walk along that path, step by step, from the initial noise all the way to the final solution image. It's a predictable, fixed-step progression.
Let's talk about the proof, the hard evidence. They tested this on some really tough problems.
They did. They picked tasks across 4 domains that require complex perception, scalable difficulty, and could be easily parsed. The exact spots where MLLMs usually fall apart.
First up was sequential planning. Things like visual spatial planning, or VSP super navigating a grid, avoiding holes, and also just classic mazes. This is where that sequential weakness of MLLMs really shows.
Oh, brutally. As the task gets harder, the MLLMs just decay so fast. Take VSP Super at level 32. It's a really hard version. DiffThinker still gets 83% accuracy.
And the leading MLLMs.
0. A flat 0%. The text-centric model just can't keep track of the visual state over that many steps. It forgets where the holes are, what it's already done. It just gets lost.
Then they went into the other areas. Combinatorial optimization, the classic traveling salesperson problem, constraint satisfaction with Sudoku, and spatial configuration tasks like jigsaw puzzles.
And in every single one, DiffThinker dominates because it can handle all the spatial constraints holistically, in parallel. The summary table in the paper table 1 just lays it all out. The overall average accuracy for DiffThinker is 87.4%.
Compared to what?
Compared to 41.3% for Gemini-3-Flash and a pretty dismal 21.1% for GPT-5. This isn't just a small improvement, it's a totally different class of performance.
Those numbers are just incredible. Let's step back for a second. What are the core properties of this generative reasoning idea that enable such a massive jump? Let's start with efficiency.
Right, because if it's not efficient, it's not practical. And surprisingly, despite being a diffusion model, DiffThinker is highly competitive. For training, its overhead is almost identical to a standard supervised fine-tuning baseline, and it's way more efficient than reinforcement learning methods.
What about inference speed? That's what really matters for users.
It's fast. It clocked in at just 1.1 seconds per reasoning instance. That's actually faster than a comparable 32 billion parameter SFT model, which took 1.4 seconds.
So it's not just more accurate, it's also faster on these kinds of tasks.
In many cases, yes.
Okay, the second property is controllability. This seems huge for reliability.
It is. MLLMs have this problem of unpredictable inference time. The chain of thought can be short, or it can be incredibly long. It might get stuck in a loop. You just don't know.
But with DiffThinker,
It's a fixed-step generative process. Whether the maze is easy or hard, the computational budget, let's say it's 20 steps of that Euler solver, is totally deterministic. You get stability and a predictable runtime every single time.
and property 3, native parallelism. This feels like the most radical conceptual shift. It's not thinking step by step.
I love the analogy you used earlier. A text model is like a person walking down a single corridor in a maze, hitting a dead end and backtracking. DiffThinker is like flooding the whole maze with water at once and seeing where it comes out first.
So in the early stages of generation, it's exploring multiple possible paths at the same time in that latent visual space.
Exactly. It doesn't commit to one path too early. It refines a whole range of potential solutions in parallel, and it uses the global constraints, the walls, the holes, to prune the bad ones. It converges on the best solution without needing to do that slow, sequential backtracking.
And the fourth property points to the future, collaborative potential. So it's not about replacing MLLMs entirely.
No, it acknowledges that MLLMs are still really good at abstract linguistic tasks, so why not build a hybrid system?
How does that work?
DiffThinker acts as the visual reasoning engine. For a hard jigsaw puzzle, it might generate, say, 5 different possible visual solutions. Then the MLLM's job is just to look at those 5 images and use its reflective ability to check them against the rules and pick the best one.
So you're outsourcing the hard spatial part to DiffThinker and just using the MLLM for the final verification.
That's the beauty of it, and it works. For a level 4 jigsaw, DiffThinker alone got 80%. But with the MLLM checking 5 candidates, that accuracy jumped to 85%.
And the MLM on its own
Got 0% on that task. So the partnership is just vastly superior. You get DiffThinker's visual precision married to the MLLM's abstract logic.
The ablation studies also gave some great insights on how to actually tune these systems. What did they find about the number of inference steps?
They found a real sweet spot. There's a clear trade-off, and the optimal balance of performance and cost is at around 20 inference steps. After that, the performance kind of plateaus.
So you don't need 100 steps. 20 is enough, which explains that fast 1.1 second latency.
Exactly. And then there's classifier-free guidance, or CFG. They call it a logic amplifier, which I think is a great term.
How does that work?
It basically helps the model focus on the task logic. They found the optimal scale was a value of 4. If you set it too low, like 1, the solution paths it generates are faint and uncertain. If you crank it up too high, to 7, you get these weird visual artifacts, and the image quality degrades.
So 4 is the sweet spot for a bold, confident, and correct path.
Precisely.
Finally, they tested the obvious alternative. Why not use video generation? Video naturally handles sequences and state changes.
You'd think it would be perfect for planning tasks. And they tested it with a model called DiffThinker Video. It can reason. It solved a maze by generating a clip of a dot moving through it. But it's just not efficient enough yet. It had a higher training cost and literally double the inference latency, 2.0 seconds, versus 1.1 for the image model.
So for now, static image generation is just the more efficient way to go for these structured problems.
It's the clear winner, yeah. The cost of current video models is just too high to compete right now.
So to wrap up the breakthrough here, DiffThinker successfully shifts reasoning from the symbolic text world into the visual generative world. It uses diffusion models to get state-of-the-art results on these hard vision tasks, and it does it with better efficiency, control, and parallelism.
But they're also very clear about the limitations. Its ability to generalize to tasks it hasn't been trained on, its out-of-distribution capacity, is still limited by the underlying generative model. It's only as smart as the MMDIT it's built on.
Which means the next big step is to build better, more robust, multimodal foundation models that are actually optimized for reasoning, not just for making pretty pictures.
Absolutely. And going back to that collaborative idea, the real future is probably a tight integration of DiffThinker's visual power with an MLLM's linguistic and symbolic strengths to tackle the whole spectrum of complex problems.
That's a really exciting path forward for AI. Before we go, here's something for you to think about. DiffThinker turns visual reasoning from a step-by-step process into this parallel image generation task that refines all possibilities at once.
That leverage of parallelism over sequentiality is the core innovation for sure.
So if that works so well for visual tasks, think about a complex text-only problem. Something like optimizing a huge financial portfolio or analyzing a massive legal document for conflicting clauses. These are traditionally sequential, symbolic tasks. But is there a way we could reformulate those abstract problems into some kind of visual or latent generative space? Could we map abstract constraints onto a diffusion manifold to use that native parallelism and dramatically speed up purely abstract reasoning? That's the big question DiffThinker's success raises for the entire field.